Okay, and here in 6.2 we're going to be taking a look at operations with polynomials. We have really three objectives. The first one I believe is probably going to be the hardest of the three, and that's to identify polynomials and be able to find the degree. Then we'll move into addition and subtraction of polynomials, then multiplying polynomials. You can look over here to the right and you can see our vocab for this lesson: monomials, binomials, trinomials, polynomials, degree, FOIL, and expand. Those are some key words there you want to keep track of as we go through this lesson. Now, first thing we got to do is we have to make sure that we know how to identify polynomials and to be able to find their degree. Well, there's really going to be a first part's monomials, which is a type of polynomial. It's a single term polynomial. So obviously the prefix mono meaning one, that's where you get your single in. Now, we got to make sure we understand the difference between a monomial and what's not a monomial. Here are some examples of what are monomials. 3x, something with a single variable, 4, constant, even a variable with an exponent, or maybe multiple variables. But no, there's no addition or subtraction because that connects terms. And so when we have something like x plus 2, we have two terms, and we're talking about a single term. And so this is not called a monomial because there's multiple terms. Also, there's some things that make it look like a monomial. If you remember back when we talked linear, this sort of falls in line because none of these are ones that we talked about weren't linear either. But none of these are polynomials, and so what you have is you have a variable and denominator. That's not a monomial. Negative exponents, not a monomial. Exponents that are fractions, not a monomial. Or even, let's say we have a variable inside of a radical. That's not a monomial, and that's key. You've got to remember what isn't a monomial, so sometimes you can identify what is. Because you're going to have questions like these down here where it says, what's the degree of this monomial? Now, when we talk degree, what we're talking about for a monomial is the sum of the variable's exponents. Now, notice I said variable's exponents, not just the sum of the exponents. It's the sum of the variable's exponents. Now, so if you take a look here, first off, the first question we got to figure out is it a monomial? That's really what you've got to decide first. If the answer is yes, it has a degree. If the answer is no, it doesn't have a degree. So we look at 3x squared and we say, well, that's a monomial. Yes. Okay, then what's the degree of this? Well, it's the sum of the variable's exponents. So there's only one variable, so the exponent is just 2. The degree on this one is simply 2. Okay. If you look at the second one, we have 4x cubed. Again, is it a monomial? It's a single term. It's not one of these. And so, yes, it's fine. And what's the sum of the variable's exponents? Well, the only exponent we have is a 3. So the sum of 3 and nothing is 3. So the degree of that term is 3. Look at this one. This right here is what trips up students. I'll put something like 2 squared x cubed, and what they'll want to put is 5. Now, why is it not 5? Well, it's because it's not the sum of the variable's exponents. 2 squared is 4. These are the exact same thing. Okay? And so what you see is, really, we want to ignore the 2 squared. The 3 is still the degree on that one. Okay? And so be very careful not to assume it's just the sum of the exponents. It's the sum of the variable's exponents. Here, even though this is negative, it's not a big deal. It's not a negative exponent. That's where we got to be worried. This is just a coefficient. So the negative 2 really has nothing to do with it. I'll get rid of it. It is a monomial because what I have is a single term that doesn't fall into one of these categories. And notice here I have a 2, and the exponent of the 1 is a 1. Or excuse me, of the y is a 1. So the sum of the variable's exponents is, again, a 3. 1 plus 2. If you take a look at a constant, this one's a tough one. And what we need to remember is going back to our exponents. Remember that a 0 exponent simply means it's a 1, multiplication of 1 here. So that's what 3 is. If I can work backwards, you can see that 3 is simply 3x to the 0. So now writing it like this, you can definitely see the degree. The degree is 0. And what you may want to just memorize is the degree of a constant is 0. The degree of a constant is 0. The degree of a constant is 0. So that may be something you want to just jot down and get your notes. Take a look at this last one. A lot of students, what they'll want to do is they'll go, oh, 2 plus a negative 3, and they'll get negative 1 as the degree. Whoa, wait a minute. This has to be a monomial first. And so if you're looking at this and you go, is it a monomial? If that's really what you ask, you'd say, wait a minute, monomials can't have negative exponents, therefore this has no degree. So keep that in mind because it does get a little tricky at times because I'll throw one of those at you ask for the degree. It doesn't have a degree because it's not a monomial. So make sure to ask this question, is it a monomial first? How do I know? It's a single term that doesn't fall into one of those kind of categories. Okay? Moving on, if we take a look at now of a polynomial. Now what a polynomial is, a poly, the prefix poly meaning many, for us it's going to be one or more monomials. Okay? So that's another way of writing this, one or more termed polynomials, is one or more monomials. So polynomials are made up completely of monomials. So if I'm asking if it's a polynomial, it has to be made up of monomials. So we have to know what a monomial is in order to figure out if it's a polynomial. So what are things that are not polynomials? Well, anything that contains something that's not a monomial. Now, how do I know if it's not a monomial? We go back to this. So any termed polynomial that may have one of those things in there is not considered a polynomial. So if we want to find the degree of a polynomial, what we typically do is we get the degree of a polynomial mixed up with the degree of a monomial. Remember, the degree of a monomial is the sum of the variable's exponents. A single term, add up the exponents of the variables, boom, there's your degree. When we talk the degree of a polynomial, we're talking about the largest monomial degree. A lot of times I say this is the highest rank. So you go, well, how many terms do I have? Well, I have one term, or I have two terms, or I have three terms, I have one term, or I have one term. So we need to look at this and go, okay, for each potential polynomial, how many terms do I have? Because I need to find the degree of each term. So here the degree of a constant is 0. There's no other terms to compare, so the degree of that polynomial is also 0. Here, what's the degree of 4? It's a constant, it's 0. What's the degree of x? 1. We're looking for the highest one. We're looking for the largest monomial degree. Well, the largest one is 1. So the degree of that polynomial, which is 2 terms, is a 1. If you look at this third one, we have here's a term, and there's a term. What is the degree of the first term? Well, it's a 2 of that one. What's the degree of this monomial? Well, it's a 1. What's the degree of a constant? Well, hopefully we're starting to memorize it. It's 0. Which is the largest? 2. So what's the degree of that polynomial? 2. Looking at this one right here, again, it's a single term made up of 3 factors, and so technically it's 5 factors here, but we have one single term. What's the degree of this one single term? Well, it's the sum of the variable's exponents, which is 4. And that would be the degree of that polynomial. Okay? One like this one, if I say, what's the degree of that polynomial? Hopefully what you go is, whoa, not a polynomial. Why is it not a polynomial? It's because it's not a monomial. And polynomials have to be made up of monomials. One more example. Let's say I gave you something like this. Just for practice, one more. Okay, and I said, what's the degree of that polynomial? Well, this is made up of 3 terms. Now, how do I know it's made up of 3 terms? Well, plus and minus connect terms. And so you can see the connection between these two and between those two. So we have 3 terms. What's the degree of the first term? Well, it's the sum of the variable's exponent. It's 5. What's the degree of the second term? It's 5. What's the degree of the third term? It's 1. So I've added up these exponents to find the degree of each little term. Now I'm looking for the highest rank. Well, 2 of them have the same rank. That means that they have the same degree. The degree of the polynomial then would be 5. I don't add those up. I simply look for the largest monomial degree. That's the difference between polynomial and monomial. This is where you might need to pause and rewind and rewatch, because this is a part of the lesson that's always hard for students to grasp, is this idea of the degree of a monomial compared to the degree of a polynomial, making sure to distinguish between the two. Here's 3 different types of polynomials we're going to work with. Monomials we've already talked about. That's a single term, so that's a 1-term polynomial. Binomial, if you look at the prefix bi, that means 2. So 2 term. We'll be using binomials quite a bit. Tri, the prefix tri, meaning hopefully you're thinking 3. So that's 3 terms and 2 terms. Okay, and so we'll be using that kind of vocab as well, monomials, binomials, and trinomials throughout this. So right now what we're doing is just talking about polynomials. Now we need to get into some more of the operations of polynomials. There's really going to be 3 operations we look at today: addition, subtraction, and multiplication. So here's your keys with addition and subtraction. It's actually pretty straightforward. You're going to combine correct terms, and that's something that you've had a lot of practice with. Just make sure that the last names don't change. So it has the same last name, Sometimes I'll refer to that. And the last name doesn't change. It stays the same. Okay, so keep that in mind. Is that it's the only things that we can combine that are what we consider like terms are things with the same last name. And those are called like terms. Okay. We don't want to treat expressions like these. Now, how do I know these three are expressions? I don't see an equal sign anywhere. There's no equal sign. If there's no equal sign, they're called an expression. If there was an equal sign, it'd be called an equation. There's a big difference between the two. And so here, we don't want to treat expressions like equations. In other words, I'm not moving things from one side to the other because there aren't sides. This is all together. This is all together, and this is all together on one side. So don't move things like you would with equations. You're just simply combining like terms. So how do we go about doing this? Well, we simply want to get rid of the bubbles. We want to get rid of the parentheses for these polynomials so that I can combine like terms. To do that, you really want to be careful, especially with the subtraction ones. We'll look at those in just a minute. Addition, usually don't do too bad. Because with addition, you don't have to do much. You can simply drop your bubbles at this point. The addition sign doesn't change any signs. And so we look at something like this, and we say, okay, well, what are like terms? So I have a 3x squared, and I have a 1x squared. Well, if you have 3 of something, you add 1 more of something, don't you have 4 of that? And so we have 4x squared. See how the last name doesn't change? I have negative 1x, and I add 4x. See, I'm not moving. I'm not adding an x here. I don't want to do that. That's what I catch students doing quite a bit, and I want to make sure that you avoid that. We're simply combining these two. And so that should make 3x, negative 1 plus 4. Then what you have here is you have positive 2 and a negative 9. Well, 2 minus 9 is negative 7. And now once you see, this is our final answer for that addition one. Okay? Not too bad on a problem like that. Let's look at subtraction. Very similar, but keep in mind what I'm subtracting is the bubble. So this subtraction sign must be distributed through the bubble. And we have a tendency not to do that on occasion. So let's go ahead and write this out with the distribution of a negative. I said 9r squared plus 6r plus 16 minus 8r squared minus 7r. Do you see the negative has to go over here? Minus 10. If you don't do that, man, you're going to be missing all those subtraction ones. I really don't want that to happen to you. Now we combine like terms. We're not moving things. I'm going to put in right here what students want to do, but don't do this. We're not adding 8r squared. Where are we moving it? There's no two sides. They're already together on the same side. I know it's a long expression, but don't move things. Combine like terms. So here and here, we have 9r squared minus 8r squared is simply 1r squared, or r squared. Now what we have is 6r minus 7r. Well, if you have 6 of something, you take away 7, you're in the whole 1. And then what we have is we have 16, and we take away 10. So it should be a positive 6. And there you see we don't have any more like terms. That's our final answer. Take a look at this last one. Again, you might pause it here, see if you can work it out, see if you get the same answer as me. But we go ahead and distribute that negative as we go ahead and write this without bubbles. And so we have 4x squared minus 3y squared plus 5xy. First bubble, not much there. Now we've got our minus 8xy. Now here's the part that we miss sometimes, minus 3y squared. Make sure to get that distribution of a negative in. Now we look for like terms. So we have 4x squared, and we have no more x squared. So we go, well, okay, well, let's put the 4x squared there. That's done. And then I notice I have like minus 3y squared and another minus 3y squared. That doesn't go to 0. Negative 3 plus 3 will go to 0. This is negative 3 minus 3, so negative 6y squared is what we have. Now we're done with the y squareds. And notice the last two that we have are right here in the middle. If you have 5xy's and you should take away 8xy's, you should have negative 3xy's. Now the order that you write this in, I would take that. That's not a big deal. Sometimes you'll see it where the x's lead off from degrees down and then the y's work themselves back up. And so you may see an answer like that as well. Or I may read an answer. These are the same answer. I wouldn't count it wrong either way. Unless they said specifically put it in some specific type of order. Which I won't be doing with you guys. Okay? Moving on. Let's take a look at multiplication. Now there's 3 types of multiplication that we're going to be looking at. Monomial multiplication, binomials, which again is 2 terms, and binomial times trinomial. This is little bubble times big bubbles, a lot of times what I say. This one right here is going to be a double bubble, and this one's just going to be a single term times a bubble. So it'll look something like that. That looks sort of funny, but that's what we're dealing with. So if you take a look here at the monomials, we're going to distribute the monomial and combine any like terms. Okay, so that's our objective here, is to combine like terms once we distribute. So let's take a look at an example here. Here you can see a monomial and a binomial, and so all we need to do is simply use what we call the distributive property. We're familiar with that. We're taking this 2x and we're going to distribute it through the bubble. Multiply it through, because 2x, what am I multiplying 2x by? Everything in the bubble. And so what you have is you have 2x times 3y, and then you have 2x times 9. You don't have to necessarily write this step. I just wanted to show you what we're doing. A lot of times I'll show this, and as long as we know what we're doing, we can go 6xy. That's 2 times 3. That's our 6, and then x times y is xy. And then over here we have 2 times 9, which is 18, and we simply have an x. These are not like terms. Why can't I add those two? The last names aren't the same. xy is not the same as x, and so we just leave it like this. That's as simplified as we can make it. Hey, another example is probably about as hard as you're going to get. A lot of things going on here, but really all you got to remember is I'm going to distribute that monomial through this trinomial and see what we get. Okay, so let's look at the first one. We have this one times that one. So first off, -5 times -3 is 15. There we go. Then a times a squared. If you remember back in 6.1, when you multiply powers, you add exponents. So 1 plus 2 is 3. And then b squared times b, again, 2 plus 1 is 3. So that's where we're at there. Next one we have is negative times a positive, which is negative. I definitely think that's a key, is you guys need to look at your negatives and positives and make sure you get the right signs there. So in this case, a negative times a positive is negative. Then you can do 5 times 6, which is 30. Then you got a times a cubed. Again, we have 1a and 3 a's. That means I have a total of 4. When I multiply powers, I add exponents. B squared and b, again, I have 2 and 1 makes 3. So a lot of things that we did in 6.1 are starting to be applied here in 6.2. The last distribution is a negative times a negative, which is positive. And then we've got 5 times 3, which is 15. Okay. Then over here we got a times a to the 4, so we got 5 a's to deal with. And notice we have 2 b's and 4 b's, so we should have 6 b's. Now we need to look for like terms, but notice none of these last names are exactly the same. And so as soon as we recognize that, you know what, those are not like terms, we go ahead and we're done. And that would be our final answer for distribution of monomials. Okay. Moving on, what we're going to take a look at here is now binomials. Now this is the one you're going to be most familiar with and most comfortable with, because you probably remember FOIL quite a bit. Now we'll talk expansion as well. That's definitely going to be something we'll talk about, but FOIL is going to be something you're going to want to be very comfortable with. You actually have some parent homework that's going to be involved with FOIL, so get ready for that as well. FOIL, this is used only when you're multiplying two binomials. When you have a double bubble where it's two terms. Now again, what connects terms? Plus or minus signs of some sort. So that's what we're talking about, is when we're multiplying two little bubbles. This allows us to sort of have a way to remember how to distribute, because it's all just distributive property. I mean, what it stands for is first, outer, inner, and last. And I'll show you what that is, but all it is distributive property. And then there's some sort of, I guess I'll call them middle school ways of doing it. And I may show you that in class. I'm not sure on the video I'll have time, but in class I'll show you that, and that way you'll see something. Maybe it'll stick with you if FOIL doesn't. So if we look at an example like this, we're multiplying two binomials. It is just distributive property. I'm going to take this p, and it's going to multiply times both of those, just like we did with a monomial. But what we can remember is first, the first value in each bubble we multiply. P times p is p squared. Then we do outer. And so what we have is something like this. And so the two outside values, which is negative 4p. Then we go inner, 6 times p, which is a positive 6p. Those are the two inside values. And then the two last values in each bubble is 6 and negative 4, so negative 24. Now once you get here, make sure to simplify. A lot of times it's going to be the two middle ones that we're going to have to simplify. In this case, that shows. Negative 4 plus 6 is a positive 2p. They have the same last name. I can combine them. Nothing else does. And there we go. We multiply those and we expand that out using this idea of FOIL. First, outer, inner, last. And again, it comes from distributive property. Let's look at the second one here. Now, we'll talk a little bit more about these two binomials, but there's something special about them. When we get to factoring, we'll take a look at them. But notice they're exactly the same other than the signs. So that means my product's going to be very unique when I'm done. Let's go ahead and go through our first, outer, inner, last. So here we go. First, 6 times 6 is 36. Then we go outer, the two outside ones. 6 times positive x is positive 6x. Notice the variables don't have to come first. I did that on purpose. I wanted to make sure you knew the variables don't have to be first. You still just do first, outer, inner, last. Inner, okay, the two inside ones is negative times a positive is negative. Careful there. And then last, a negative times a positive is negative. X times x is x squared. Then we looked, and again, the two middle ones. Ooh, there it is. That's what makes this one so special, is that those two middle ones cancel each other out. And then what we have is 36 minus x squared as our final answer for this one. It's actually called the difference of two squares, and we'll talk about that down the road a little bit. Right now, though, we'll move on. Here's another binomial times binomial. So anytime you have this situation with little bubble times a little bubble, what you do is you FOIL. Little bubble, little bubble. And so what we do is we do first, outer, inner, last. It's distributive property. First, 3 times 2 is 6. Ooh, a squared times a, multiplying powers, you add exponents. Outer, 3 times 3 is a positive 9. A squared, b squared. Can't do much there. Inner, we got a positive 4ab. And then last, what we have is a positive 6b cubed. Is what we have, b times b squared, multiplying powers, you add exponents. Then we look to see if there's any like terms, and notice in this case, there isn't anything. Everything is its own last name. A cubed, a squared, b squared, ab, and b cubed. So, that's as far as we can go. That's as far as we can go. And so we circle that, and that's our final answer for foiling. Okay, multiplying two binomials. Be proficient with that. We'll have some more practice even on this screen, because on this screen what we're going to be taking a look at is an expansion. Now we use an expansion when we have a little bubble raised to a power. So let me give you an example. Here's a bubble squared. Or here's another bubble squared. It could be even a bubble cubed. Now we won't do a lot of these necessarily, but it's sort of the same type of problem. We want to expand it. And here's the key, and I have a star next to it, and it says this: never take an exponent across a plus or minus sign. Now what we do is we get it a little bit confused with power over product. Sometimes we have this. And what we do is we share it, right? That's what we did in 6-1. We shared that exponent throughout that bubble. However, with terms, we cannot do that. We cannot share this across a plus or minus sign. I always make students, if they do that, they have to bring in snickerdoodles for me, because that's the cookies I enjoy. So if you end up trying to do it like this, where you go, it's x squared plus 4, I just squared the x and squared the 2. Unfortunately, that is not right, and you're going to be owing me some snickerdoodles. So hopefully you don't make that mistake, so you don't have to bake anything for me. But you need to keep that in mind. Never take an exponent across a plus or minus sign. Okay, that's just something that's going to keep popping up. Don't confuse it with your exponent properties. Now let's talk about this expansion of the bubble, and so we can FOIL. And then we'll, again in class, we may look at the middle school ways of glasses and bunnies. They're pretty funny. But if we take a look here, what we have is a bubble squared. There are no tricks here. What you want to do to solve this is expand it. That's the best way. That's how I want you to do it, is expand and FOIL. Now we've already done FOIL, so I'm going to do this a little quicker. So first, outer, inner, and last. And then combine your like terms, and there you go. There it is. Now, again, if all we did was go x squared plus 4, and we took it, notice we're missing our linear term, that middle term. So that is not going to be good. We do not want to take an exponent across the plus or minus sign. Here's another example. I cannot just square the 2x and square the 3. I wish you could. It'd be so easy. Unfortunately, we can't. Let's expand. Okay. Anytime you have a bubble raised to a power, you want to expand. Expand those bubbles out. Now FOIL. Again, it's going to be 4x squared. 2x times 2x is 4x squared. Then I get minus 6x. Minus 6x plus 9. Again, the FOIL I'm going a little quick on. You need to make sure to slow down and make sure you're getting the same answers I do. I encourage you to pause the video before I get these answers. Go back and pause them. Make sure you can get them. I know I can. Hopefully you can too. Here's the last one we'll take a look at again. You cannot take an exponent across a plus or minus sign, or you owe me snickerdoodles. So what we can do though is we can expand it and use a FOIL method. So we got first. I'm going to put this in black so you can see it. There we go. First, x squared. Outer, minus 3xy. Inner, minus 3xy. And last, positive 9y squared. These do not cancel. Remember, the only times they cancel is if I go back a screen here and show you these things right here. And these are called conjugates, and we're not necessarily learning that right now. but notice they're exactly the same except the signs. When we go to the expansion, they're exactly the same. So there's never a time where the outer and inner are going to cancel each other out. They're always going to create a new term right there in the middle. And so we want to expand and then combine like terms, x squared minus 6xy, because if you have negative 3 and you take away 3 more, you have negative 6. And the last name does not change when you combine like terms. Okay? Taking a look here really at the last thing is a binomial times trinomial combo. And again, everything that we've been doing is distributive property, but this one really is going to show it. Because there isn't a method like FOIL for us to necessarily do. You might be creative and come up with your own. That would be pretty cool. And if it catches on, I'll end up using it. But what we need to make sure to do is anytime we have a binomial times a trinomial, or like this one, a trinomial times a binomial, we want to go ahead and just distribute. There's a few ways you can do this horizontally or vertically. I like the horizontal. That's what I'm going to show you. So what we're going to do is we're going to take this x right here, this positive x, and we're simply going to distribute it all the way through. And so we have x times x squared, which is x cubed. Multiplying powers, add exponents. Then we got negative 2x times x, which is negative 2x squared, excuse me. And then we've got a positive 3x there. So the x has been distributed. Now let's go ahead and do the positive 1. It's going to get distributed all the way through as well. So what I get is a positive x squared, a negative 2x, and a positive 3. So x squared, a positive times a negative is negative, positive times positive is positive. Now we look for like terms. There are no other x cubes, so it's done. Here we go. Negative 2 plus 1 is negative 1x squared. Remember, last names don't change. Oh, here we go again. Okay, 3x minus 2x is a positive 1x. Boom. And then we have a plus 3. Remember, we're not moving things. When we are simplifying expressions, it's not about moving. It's about combining like terms to simplify that expression. Don't treat it like an equation because it's not. Last one. Okay, and this one actually works out really nice when it's a trinomial times binomial. But what we want to do is take this first term and distribute it through the little bubble. And so what we get is x cubed minus x squared y. Then we do the same thing with the positive xy. And we distribute there. And x times x is x squared, and I got that y. Then I've got a positive times negative, so negative. Don't forget to look at that. And then you got xy squared. Okay, y times y is y squared. Now we got the last one. I got to distribute it through. I get a positive xy squared. Excuse me. And, oh, I almost made a mistake there. And a positive times a negative is a negative y cubed. Watch your signs. I almost did the same thing. It's a negative. Now combine like terms. You can see where this one works out really nicely because, look, boom, boom, those cancel each other out. If I had negative 1, I add 1, it goes to 0. Ooh, there it is again. Okay, and it's gone. And look what we have. That's all we have left is x cubed minus y cubed. That's a very special one too. When we get to factoring, what we'll learn is that is called the difference of two cubes because it goes to the difference of two cubes. And so this right here is a sort of special one. But right now, all we need to make sure to know how to do is distribute, combine like terms, and again, make sure that we're down. We understand the vocab words with polynomials, monomials, and degrees, binomials, trinomials, and then make sure we know how to FOIL, expand, and then distribute on this.